everyone. This is Steve Williams with the Right Approach Consulting, and today I've got industry veteran John Johnson with us, and we're going to be talking about a special process called A-SAP. John's currently the VP of Business Development and overseeing quality at American Standard Circuits, and they're one of the early adopters of this technology and license holders. So, John, welcome.
Thank you.
So in the nature of full disclosure, we're going to be putting up some slides that say confidential, but we have both American Standards and a Veritex permission to use these slides. So let's take a look at a couple things. And first off, what does A-SAP stand for? What does it mean?
Well, A-SAP, the A in A-SAP stands for Veritech. And of course, SAP is a semi-additive process. So it's a Veritech semi-additive process, which they've developed for the electronics industry, predominantly circuit boards. But
okay, very good. And you're prior to you've had a lot of leadership positions in the industry, but prior to American Standard, you actually worked at a Veritech.
Right, I was the vice president of sales and customer support, and my role there predominantly was working with the licensees to get them up and running, and to kind of bring, product realization to the forefront with them.
Sure. Okay. Very good. Us old board rats, I remember way back in the day that the additive process, fully additive process, is a pretty old process. And that was back when they were making print and etch boards and, 15 mil line width and space. So what's the difference between additive and semi-additive?
Well, semi-additive really is similar, but not. Mm-hmm. With an additive process, back in the old days, those processes would run in plating 24 hours or more to get the right plating thickness. But in this process, we are putting down a very thin layer of electrolysis as a base metal, rather than using an ultra thin foil or something like that. And once that's defined, then we'll go down with a photoresist and image trace patterns in there, which are actually trenches in the resist. And then we go ahead and we'll plate those up and strip away the resist. And there we go. We'll just flash etch the base electrolysis copper. So it's not touching the circuit walls at all. It really looks like an additive type trace, but it's plated up inside that trench, so you get perfectly straight sidewalls and a lot of benefits towards signal integrity and things like that.
Excellent. Let's take a look at the slide here that you've got about the chemistries. Talk a little bit about that and what kind of applications this process typically is made for.
Well, this process really works well for anyone trying to define a very thin lined trace. And, it works for ultra high density circuit boards. And in fact, that's what we call our program, is ultra high density interconnection.
Okay.
And if you look at any high performance HDI circuit boards, they can benefit from this technology, where you have something sub 75 micron trace and space, the old 3 mil and 3 mil lines and spaces. If you have a 2 mil and you have, let's say, VN pad plated over, and you have multiple plating steps, this technology can help in that even, so it's pretty broad ranged. Package substrates and interposers. I mean, if you look at that technology, there's a lot of buzzwords floating around out there right now in the US, because they're bringing back this technology here to allow for supply to critical industries, defense, aerospace, where we're not so dependent on the Far East. But when you look at this, it requires traces that are going to be sub 25 micron, sub 1 mil. So, that this chemistry will work well for that. And then passives, inductors, capacitors inside of the boards. Now, capacitors, resistors, and so forth have been around. That technology is not new, but certainly this can be done in a different way, where you're building traces that are very tall, but very narrow, so that your aspect ratio and spacing ratio is tight.
Sure.
Also for antennas, waveguides, there's lots of different aspects that Veritech has worked on to grow this into different passives. And really for the future, they're looking at ways to embed chips. So it's pretty exciting.
That is exciting. Well, I remember when 3 mil line of space was the state of the art.
Right. Or the bleeding.
The bleeding edge.
Bleeding
Yes.
edge. Yeah.
Yes.
So,
Exactly.
yeah, it's nice to see this type of technology come around, because it certainly gives us a chance to get that leapfrog over where Asia is at today.
Sure. So let's talk a little bit some of the advantages of this technology.
Well, when you look at the circuit board in general, today we're kind of locked in at 3 and 3, and some folks can do 2 and 2 in lines and spaces, but maybe some cases it's by accident. So but if you get down to 25 micron lines and spaces, 1 mil line of space, you can actually reduce the size of the circuit board. Already the chips have gone smaller and smaller in terms of pitch. 0.5 millimeter BGAs are fairly common now, and all that we hear, it's going to go down to 0.35 and then 0.3, and who knows from there. Well, you can't route that out of a pattern very easily with even a 2 mil line in space. You have to get down to the 1 mil line in space. So that helps. But when you're doing that, you're reducing layer counts, you're reducing the number of microvias in a structure, which can improve on reliability. You don't have to have as many stacked microvias. So, we looked at situations when I was at a Veritech of reconfiguring 12-layer boards with many subassemblies down as far as a 2-layer board. So it's really quite amazing what you can do to go to the ultra-fine lines in space.
Oh, absolutely. Absolutely. And American Standard's a big RF manufacturer.
We are, yep.
Big application for this in that niche, right?
Yes, absolutely. From a signal integrity side, and getting that straight sidewall, it benefits a lot. But also, this technology works very well to produce very, very low surface profiles.
Okay.
So that is an additional benefit. Looking at just building boards with controlled impedance, you can get to a lot tighter tolerance on that. We talk about in our industry, well, plus or minus 10%. It's but well, we can do 5% when we practice a little bit. Well, this can get you down to much tighter tolerances the first time out of the box, because you're building right to the design that was supplied, and your trace is going to be right there. And since you're plating a trench up, that little trench gets filled up, and that's exactly at the width that the designer intended. So it's a lot easier to hit the impedance requirements. The other neat thing about this technology is it has a pretty big potential in the medical industry. You can make biocompatible circuit boards, and what we can do is not have any copper or any nickel, which are toxic to the body, in the construction completely. So you can do traces that are all noble metals, palladium, gold, and so that it's a big improvement there.
Are you guys doing any biocompatible stuff now?
We are.
Yeah. Okay.
Yes. Yeah.
Excellent.
Yeah, we've built a couple of programs here, and more to come.
Okay. Very good. So one of the foundations is LMI, right?
Yes. LMI is short for liquid metal ink, and that's a Veritech's chemistry, patented chemistry for putting down a very, very thin coating of palladium on the surface. And that palladium is a very dense coating of palladium, basically atoms touching atoms, and it's several levels deep of atoms, and so a few nanometers thick in actuality.
Hmm.
And that density really helps in getting a plating down into all the small crevices and small vias that need to be plated. The liquid metal ink is a non-aqueous base to it, and so that wets very, very well in all the little nooks and crannies that you'll see in drilled holes and things like that. So you can metalize these holes, if anything, easier than standard chemistry. Now, bear in mind, we still do use electrolysis from a variety of manufacturers. So this doesn't replace electrolysis. What it does is it creates that catalyst level that you need to get the plating accomplished. And it also works with different metals, though. Liquid metal ink could be with gold, could be with silver, palladium, platinum, so forth. So it's just not for palladium in this case.
Okay. That's pretty interesting. You look at the comparison between the standard process and the LMI process, it's striking.
Right. Yeah. So this slide kind of illustrates what happens in a standard process where you have palladium deposited out of an aqueous solution that is kind of dispersed, and the copper tends to build slower, and it's less dense during the immediate stages of plating. And over time, it'll build up a thickness dense enough that it'll support a electrolytic copper plating. Whereas with the LMI technique, you have a very dense level of palladium that you see in kind of illustrated in the picture here. And you can plate electrolysis in a very thin deposition that will be able to conduct electricity for electroplate. And that's the key differences here. If you see that SEM photo up in the upper right, that actually shows the electrolysis deposition, not the palladium. The palladium's so fine you can't really see this in an SEM. You'd have to have a transmission electron microscope to take a look at that. So, but if you look, you can see how fine the electrolysis deposition is and how it actually has followed the topography of the copper foil that was there beforehand. And that helps to give very, very good adhesion to that surface.
Excellent. So before we put up another slide, just a baseline question. Is it a special process? Can board shops use their existing process and equipment and tanks, or do you have to put anything special in place?
Well, that's kind of the interesting thing is with this technology, there's very few tanks that have to be put in place to get set up. There's very few additional lines to be run. You can use existing lines for flash etching. For example, we use our interlayer clean line, which has a micro etch in it, to do the flash etch. So it functions quite well. But if you look at it, it just the whole process is just using different photoresists that have the resolution capability down in the 25 micron range. And as long as you have a photolithography available, like a Orbitech unit that goes down at 25 micron, or what have you, one of the LED units, you have something that can resolve down and make the narrow lines.
Okay, so it's not quite a drop-in, but pretty close.
Yeah, pretty close. Yeah. In fact, I can show you some examples. Maybe I don't know if you have them in the slides, but we put this in at the Navy. They had been one of the early adopters, and in 2 weeks we were running panels there that had 25 micron lines in space. They had the capability with their photolithography to get down farther, and within another few weeks after that, we were running 15 micron, actually 12.5 micron half mil lines in space. And let me tell you what, as someone who has been in this industry a long time, it brought tears to my eyes. It's just beautiful. It's beautiful. And that spiral pattern we did was just awesome. It was no shorts, no opens. It was just really good. So
Wow.
yeah, the slide you're showing here kind of is a comparison between the A-SAP process and the ultra thin foil processes that are sometimes called M-SAP in Asia and so
Okay.
forth. But what we have here is kind of showing the difference. In the older M-SAP processes, they started out with a 5 micron foil, kind of an 1/8 ounce copper, as we would call it in the older
Okay.
days. But and now there's foils that are 2 micron and even as thin as 1.5 micron. And when you go through that, you're still dealing with a fairly thick base foil that you have to etch.
Right.
So when you etch something that is, only 0.2 of a micron base, it etches very quickly. And that flash etch, I referred to, is really what happens. It etches so quickly it doesn't touch the electroplated sidewalls. But when you're etching a copper foil that is 5 micron or 2 micron, you still do get some attack on the sidewall, and you don't get a perfectly vertical sidewall, or you don't get a trace that's exactly 25 microns. So you have to make adjustments more in a more traditional fashion, if you will.
I mean, talk about your straight edges. This is incredible. This is really staggering to look at how straight those line width edges are.
Right. And on the left, you see the trace that's been plated, and it still shows the electrolysis down at the base. And you can see how thin it is. This trace here is 11 microns wide, and it's about 27 microns high, I believe.
Wow.
And when you go and do the flash etch, you look at that trace, and it's like it hasn't been touched. So it's really amazing.
It is.
And yeah, it's hard to beat that sidewall. So
yeah, that's just phenomenal. I mean, I remember way back, all the rules are kind of out the door now with aspect ratio and surface to hole plating, because this really is a game changer.
Oh yeah, definitely. So a lot of it, you talk about, you're going to bring up design benefits coming up, but I mean, it's really amazing what you can do with the technology. There are some things you have to watch out for in a design, and because you can do the ultra fine lines and spaces, a designer has a lot of things in their toolkit today. You have VN pad plated over, you have microvias, you have stacked microvias, and all these different structures. But when you're designing with A-SAP, what you really need to focus on is using that ultra fine line width technology first, and then going to the other aspects, maybe using just staggered microvias or several levels of staggered microvias, and then going to, if you really have to, a stacked microvia. And that gets away from some of the reliability traps we've had to deal with because we couldn't get to those ultra fine lines.
Okay.
The slide you got up here is kind of showing what happens when you can get down with this technology. And present subtractive technology really is around 75 microns, 3 mil lines in space. As we mentioned earlier, some folks can get down to 2 and 2, but it isn't without some challenge and yield penalty. This technology allows us to get to 25 microns, which indeed is the present semi-additive capability in Asia. And they, from what you hear, they tend to struggle at 25 micron. It's not a slam dunk, certainly, but this technology allows to take it even further into the 15 micron, 12.5 micron range. And ultimately, Veritech's working in a next generation of products down in the 5 micron range. And that's really where you get into the semiconductor range right there. And certainly with packaged substrates, they'd all love to have that capability today. So
for 25 microns, that's 1 mil, right?
That's 1 mil. Yeah.
Okay.
Definitely.
So the sub 1 mil is 15 microns and 5. That's almost hard to believe that we can get there, but we'll
Yeah.
wait for this process to come out. That's
Yeah.
incredible.
Yeah. Well, like I say, the 15 microns I've already run in a fab facility, and it's doable, and certainly with yield. So that's the amazing part. So we're actually headed that way ourselves here in a not too distant future.
Okay.
Yeah,
So
these
it's kind of a
these
visual reference of what you just talked about, right?
right. Yeah. So if you look at the first spiral, that's a representation of the 3 mil line in space, and that's done in a subtractive format. If you look at the 25 micron, now you get a 9 times increase in density, and you can see that that line is pretty uniform. And then you go to the 12.5 micron half mil line in space, and that's like I said, is you look at that under a scope, man, oh man, it is beautiful.
I've seen some
So,
of your samples, and you're right. You got to have some kind of a scope to even see this definition.
oh yeah, absolutely. Yeah, it is very hard to see. Can't use a 10 power eyepiece and expect to see it very easily. So,
Absolutely. So, I mean, this is just, it smacks you in the face looking at this comparison here.
right.
So the circuit density and improvement, how has this been accepted and used by the design community that are putting out new designs that people like American Standard have to build?
Well, that's where things are still in largely the development stage.
Okay.
There's a lot of designers that are looking at it. In the DoD, there's designs that have already are out there, but it's really taking and bringing this to the marketplace with designs that are designed for the fine line and space features. And there's a lot of them out there today, but there's a lot of cases where people are still trying to get over that hurdle in routing out of the fine pitch devices. And as soon as they start utilizing this technology, they're going to find how easy it really is.
Interesting. You had mentioned some work you did for the Navy. I'm not sure which ones are referencing that, if they're even in this presentation, but this is an interesting slide here.
Oh yeah, this is a sample on liquid crystal polymer material, and it's showing a 4 mil thick substrate here, 100 micron thick substrate, and it kind of shows how far away these traces actually can be from a plane layer, where they can actually be very tight, very close to each other. 17 micron in this case, and 11 micron wide traces, 13 micron high. So I mean, they can have a lot of electrical effect with each other, differential pairing, because they're so tight, and that ground plane is so far away.
Mm-hmm.
So it's has very little effect at that point. So.
And you talked a little bit earlier about biocompatibility. This is just a good visual that this stuff works with just about any combination of those metals.
Right. Yeah. It's that's the beauty, is you get the noble metal that is stable inside the body, and if it's on an LCP or polyimide material, folks are using that now in neural probes and glucose monitors and other type of implantables. So of course, you see it on TV every day. Glucose monitors are out there, but
Mm-hmm.
when you can get something without copper, without nickel, it makes it a lot easier to stay in body a lot longer. So.
Sure. Talking about the design guys, I work with one of your primary design houses that you work with, Freedom CAD, and we talked about this at the last webinar we did with them, and they're very aware of this technology. They are incorporating it into other designs that come across that are new, where they're looking to reduce or improve performance. How do you get the word out to everybody else that needs to know that this is a viable option now?
Well, we've had a lot of seminars with our customers,
Okay.
Certainly in discussions like we're having here today, the line is being commercially built, and so that's part of the key, but also in putting together design guidelines, recommendations. It's things you have to watch out for when you're building parts. Enig's a great finish, but when you have a 1 mil line in space, well, you put 2/10 of nickel down, all of a sudden that's a 6/10 mil space. So it does get a little bit more interesting.
Right. And I found this incredible that from a design standpoint, you can eliminate virtually 70% of the ball or solder connections.
Right. Yeah. And when you start looking at it, a lot of times you can get rid of that redistribution layer and you can actually solder right down to the chip, so it's really pretty amazing.
Well, John, this has been a fantastic discussion. It's just amazing, this technology, and it's something that even 10 years ago nobody could have even dreamed about, right?
Right.
And you guys are making it happen. Very exciting.
Yeah, that's the fun part of it, and it's what I enjoy doing. I mean, in this part of my career, the ability to bring this to a point of reality is just fabulous.
Great. Well, John, I appreciate your time and your expertise on this, and we'll be talking to you soon.
Thanks, Steve. Appreciate it.
All right. Thank you.
Thanks.
Very good.